All right, so we're on our third lesson for chapter 8. This over here. And we are comparing simple and compound interest. So what's the difference? We've kind of looked at the difference already. We know that compound interest continues to include money that is earned throughout the period. Okay. Well, let's look at the table of values. Now the table of values for simple interest, you can look at it and you can calculate first differences, right? Because if its first differences are the same, what kind of function is it? It's a linear function. And you can see, I'll post these as well, but you can see for the first differences, it's really easy to calculate. You go up $50 every year, so the first differences is $50. In fact, your first differences is just your interest. And then you can do the same for your compound interest, which is the examples we did in the last two lessons. So for compound interest, again, your first difference is just going to be your interest for that year, because that's what you go up by. And so let me just write this down. So our first difference is, first it was 5250. And then 5513, 5788, and 6078. And I'll post my solutions as well. Now your second difference is, well, you can do this minus this, and when you do that, you get 263. Okay, for again, final minus initial, and you get 275. And again, final minus initial, you get 290. So our first differences aren't the same, and our second differences aren't the same. So it's not linear, and it's not quadratic. Could it be exponential? Now here's the interesting thing. Right, let's look to see if there's a common ratio. Right? It doesn't matter whether you do it in the first differences or the second differences, right? You can do 55.13 divided by the previous 52.50. And if you do this, you'll see it will be equal to, you can do it later, this divided by this, or this divided by this, or you can even do it in your second differences, this divided by that. For example, 2.75 divided by 2.63. If you do it, it won't be perfect, and the reason why it's not perfect is because when we did our calculations on our table, we always rounded off to the nearest penny. Okay, but if you never rounded off anything and you kept all your digits, it would be perfect. And it's 1.05. Isn't that interesting? Because our interest rate is 5%. And we'll talk about that a little more on the next page. Now the next page starts by saying, well, graph them. This is really tricky to graph. I find it a lot easier to visualize it on Desmos. So that's why I have Desmos open. And I punched in the values for our years and our ending balance for our compound interest example. And you can see it right here. Now it almost looks linear. But what if I were to plug in, say, let's add another table. And we'll do 1, 2, 3, 4, 5. And we'll do our simple interest example. So we got 1050, 1100 going up by just 50 every year. Okay, so our black example, which is our linear example, which we've shown by seeing the first differences are the same. If you remember how to create an equation, we can actually show you. So that would be slope is 50x, and we started at 1,000. There we go. So that blue line is our linear function for our simple interest, which goes through all of our black points for simple interest. Notice that the green points, which are compound interests, right, initially are very close, but then move further and further and further and further away. So when you look at it like this, you can clearly tell they're diverging. It's not linear for sure. And in fact, because we've shown that the common ratios are the same, this is an exponential function. And in fact, your common ratio, right, which is 1.05, for the question that says what seems to be the relationship between the common ratio and the compound interest, well, that is just 1 plus our compound interest, which in our case r is 0.05 or 5%. Let me make this bigger. I don't know if you can see that. Okay, so that would be just be 5%. Now, if the bank was saying the compound interest was 6%, well, what would be our common ratio? If it was 6%, our common ratio would change to be 1.06. Okay, so we do have an equation which can help us with compound interest. And it is actually say P, which is our principal amount after a certain number of terms or period, equals P naught, which is our initial amount, times 1 plus R, where R is our interest rate, to the power of N, where N is the number of times that interest is paid, or how many periods we have. Does that equation look familiar? It was what we did right at the end of chapter 7 for exponential growth. Same equation, except when I'm saying amount, well, everything we're talking about is dollars, right? So that's what I wanted to go over. And we'll do one more lesson, which I will talk about present value and future value, and a couple problems with that. Okay, and I'll also then put up a Google form on Wednesday, which will sort of go over all of our interests. Okay? And then we're done the course. See you tomorrow.